Hello guys. Let's quickly go through all the problems of today's weekly contest for 26. So I have solved all four. We will go through one by one. So let's go through the first problem. So this is like smallest number with all set bits. So what we need to answer here, like what is the next number which is just greater than or equals to n with all bits set. So which number has all bits set? If you consider 1, 3 and 7, 15, so all these are some powers of 2 minus 1. So this is 1 is basically 2 to the power of 1 minus 1, 3 is 2 to the power 2 minus 1, 7 is basically 2 to the power 3 minus 1, like that. So all we need to do is like what I have done. We can do a binary search from 0 till 10. Why I'm taking 10? Because the maximum limit of n is given as 1000, right? And 2 to the power 10 is 1024, 1024. So at max we need to check on the till 2 to the power 10, and we can keep our answer as n because the answer will be greater than n, right? So we did a binary search to find uh, I did a binary search to find the minimum power which is greater than or equals to n, and we did a minus 1, right? So this is basically 2 to the power mid, right, minus 1, so that is considered num. So if that num is greater or equals to n, then that will be considered as an answer. Like if you consider here, so when it will go to 16, so num will be 16 minus 1, that is 15. So if that is greater than or equals to 10, then we will consider 15 in our answer, and go for searching on our left half, right? So like that. Let's go to our second one. So this is basically, in this question we are given an array of n integers, and every there are n minus 2 such elements whose sum is represented by one another element, right? So those make n minus 1 elements, and the rest one element is a special number, is an outlier, that is defined as an outlier. So basically what we need to check, like if you consider this array, so here if you consider these n minus 2 elements, so their sum is represented by this element, right? So basically 2 plus 3 is 5, and this 10 is the outlier. So you have to check like which can be the maximum outlier in nums, because there can be like multiple outlier elements in nums, right? So how did we check that? Like here you can see minus 3 minus 1 and minus 2 makes minus 6, and this 4 is the outlier element here, right? So what we have taken, like for checking whether that number is present in the array or not, we have taken this map, and these are basically the variables. So here I have taken count, like a particular element is appearing how many times, and here I have taken the sum of the whole array, right? And after that I have checked through all of the array elements, like checking possibility for each and every element whether it can be an outlier element or not, right? So for that what we need to do, we need to exclude that element from the total sum of the array, right? Because if you see this 10, this 10 is not contributing to the calculations of sum, right? Because these 2 and 3 makes 5 which is equal to this element, right? So there is no role of this element in those sums, right? So what we do, we first exclude that particular array of I from the total sum, so we consider it as current sum. Now if you see here, this 5 and these two elements also makes 5, right? So if we sum up them, it makes 10. So the current sum should always be equal to an even number, right? So if that current sum is odd, we can just skip it, because it can't be, then a of I cannot be an outlier element, right? So now we come to our required sum. So if the required sum is obviously current sum by 2, because here you can see 5 plus 5 is 10, so the current required sum will be 5. So now what we do, we check that if that required sum, that if this 5 is present in the array or not, because we are now we are on this 10, so we need to check whether we have previously encountered 5 or there is 5 somewhere else away, like ahead from 10. So for that we have here we have taken count of all the elements which are present in the array in a map, and now we are checking if that required sum is present in the array, then this basically checks if the element is present or not in the array, in the map, sorry. So now we will check, like if now there can be two conditions, like if the required sum, like whatever we are searching for, we are on that element only, like the current element is also equal to that. Like let's say if this 5, if this is also 5 and this is also 5, this is not 10, if this is 5, then it can be the case that required sum is equals to a. Then what we need to check, that if it is occurring twice or not, because we have to exclude this outlier element, right? So it has to occur more than once, like at least twice. So that's why I have added a check here, that if required sum is equals to a of I, that if the outlier sum and the required sum are equal, if the outlier element is equal to the required sum, then we need to check if then we can consider that an outlier element, right? Then I am taking that a of I into consideration of calculating outlier element. And if it is not the case, like if this 10, if this is something else rather than 5, then we can just compare it with our answer, right? So that's the whole thing, and at last we have returned our answer. That's it. Let's go to our third one. This one I found even more interesting than the final one, since the constraints of this problem were a little loose, like up till 1000 only. You can see here the nodes, number of nodes in the tree are there. If it increased to, let's say, 10 to the power 5 or 10 to the power 6, then it needs some different types of algorithms, like DP will be needed, but that's okay. Let's go through the problem. So you are basically given two trees with n and m nodes respectively, ranging from 0 till n minus 1 and 0 till m minus 1. And you are given the edges of the tree, and so this part is basically explaining that only. And you are also given an integer k, and now there is a term in this question called target. So if node u is a target to node v only if u and v are at a distance less than or equals to k, right? So since it is a tree, there can only be a single path between two nodes. There will be a unique path. So we need to calculate, like how many nodes are there within a distance of k from that node, and the number of all such nodes is called, the number of all such nodes we have to calculate for any answer of I. But the twist here is, like, you can connect, if you have to connect one node from the first tree to any other node in the second tree, right? So what we have to observe here is like if we have to maximize our answer, then in the first tree we can't do that, right? Because in the first tree answer will be fixed. Like for a particular node, how many nodes are within a distance of k, that is fixed, right? We can't change that. What we can change in the while this like connecting one node from the first tree to any other node to another node in the second tree, right? So if we like let's say we want to connect some node to the other node to maximize our answer, so what should be the what which node we should prefer? We should prefer the node which has maximum number of nodes within a distance of k minus 1, right? Because one distance we have covered from the node connecting the node in the first tree to the node connecting in the second tree, right? We have covered one distance, so how much distance we are left with? We are left with k minus 1. So we will try to find the node which have maximum number of nodes within distance k minus 1, right? Hope you get the point. Now it is mentioned that all the queries are independent, like for each node you have to calculate independently. So here the edges are given and k is given. So for each node you have to print like how many nodes are within a distance of k if you connect one node from a node from the other tree, right? So yeah, one more thing to notice here is we only have to connect that particular node for which we are calculating answer to to another node of the second tree, right? So only then it will be making a distance of k. Like you see, we try to maximize the distance value in the second tree also, right? So which maximum value we can take? So one value will be the minimum for connecting first tree to the second, because one node needs to be connected. So we will be connecting the node for which we are calculating the answer to the that particular node which has maximum number of nodes connected within a distance of k minus 1 in the other tree. Hope you are getting my point. So for that we have just taken two graphs and two vectors of c1 and c2. These basically represent like c1 of I will be representing how many nodes are within a distance of k from that node in the first tree, and c2 is the vector which counts how many nodes are there in the second tree within a distance of k minus 1 from that node, right? So c2 of I will be representing how many nodes are there within a distance of k minus 1 from the node I in second tree, right? So here we have constructed that graphs g1 and g2. G1 is the first tree and g2 is the second tree. So now we have resized our c1 and c2 as 0 0, and we have run two bfs, right? So this is for the first tree. So this has gone of n square approach, because for every node we are calculating like running bfs and calculating how many nodes are within a distance of k. So this is for the first tree, right? This part up till here is the first tree. And how we are doing it, we are taking a pair of int comma int, so it will be storing the node and what distance it is from that I, right? So if we are considering the node current node I, then it is from a distance of 0 from itself. So I am pushing q in the queue I comma 0. So now I am running a bfs, so I am iterating all of those nodes that are connecting to that I, and if that is not visited, I am increasing the distance and pushing it into the queue again, right? And if the distance at any time goes beyond k, then we will just break the iteration, right? So this will create our And at last I am representing c1 of I equals to result, which means that result number of nodes are there which are at a distance k, which are within a distance k in the first tree from node I, right? Similarly I am doing from similarly I am doing for the second tree, but here the twist is I am checking for only a distance of k minus 1, right? So only up till k minus 1 I will be counting how many nodes are there, and I am taking it into c2 of I, right? Now what I need to do, what I have to check, like which node has most number of nodes within distance k minus 1 in the second tree, right? So for that I have taken two variables. This result g2 is the node and this mx is the maximum number. So we don't need this variable, but for the sake of your convenience I have taken so here we have calculated what is the maximum number of nodes that are connected for a particular node within a distance k minus 1, so that is stored in mx, right? Now for every node what we need to do, like we have to just sum c1 of I and mx, because what c1 of I is storing, c1 of I is storing the number of nodes for node I. How many number of nodes are there in the first tree that are within a distance of k, and into that we are adding how many nodes are there in the second tree for what is the maximum number of nodes that are connected to a particular node in the second tree within a distance of k minus 1. So yeah, that finally make our answer, and that's it. So let's go for the final one. So I didn't read the question properly. I was just thinking like it's just the first problem with some different constraints. So I was trying to do some random DP, which I found later was incorrect because of my bad approach of not reading the problem. So yeah. So basically this problem is like how many nodes are there. The condition is almost similar, just one condition is different, you have to count the number of nodes which are at even distance from a particular node. For every node you have to calculate how many nodes are there from even distance from that node. And that connection problem is similar, like you can connect one node from one tree, from the first tree to some other node in the second tree. And again the queries are independent, so you have to calculate for each node independently. So like here one thing to check is for like again in the first tree you can't change the answer for any node, right? So like if you make the graph a bipartite graph, like if you color every node either 0 or 1, or let's say either 1 or 2, then it will make it bipartite, right? So all the nodes which are having colored, like let's say if you are painting them with 0 and 1, right? So all the nodes that are painted 0 will be at even distance from each other. Like if you take any pair of nodes which are painted 0, they will be at even distance, and all the nodes that are painted 1 in itself, they will also form such pairs which are at even distance, right? And all the nodes which are having pairs of colors with pairs of different colors, like if you pick a node with 0 painted and painted 1, then they will be at all distance, right? So in the first tree there will be a fixed number of nodes that are at even distance from each other, right? So what will be that? That will be the count of nodes that are painted 0, right? So similarly in the second tree, now you can see what we will do. In the second tree we will also make it a bipartite tree, and then what will be, how we will be checking, like we have to again connect one node from the one tree to some other node in the second tree, right? So what I tried to do, like to find whether what is the maximum number of what is the maximum number of nodes that are painted 0, or they are painted 5, or they are painted 1. Like if the number of nodes in the secondary that are painted 0 is greater than number of nodes that are painted 1, then we will try to connect the that particular node from the first tree to some other, to some adjacent node of that zero painted node, which has, like if I try to draw it, okay, I can't draw it here. Like let's say some node is painted 0 in the second tree and number of nodes painted 0 are greater. So we will try to connect one of its adjacent nodes which are painted 1, right? So that's what we are doing here. Like in the first tree, I am just putting like their colors. Here I am making a bipartite graph using BFS, and these are the values. Like in the first tree, how many odds are there and evens are there, like 0 and 1. You can say like how many odds are nodes are painted 0 and how many nodes are painted 1 in the first tree. Similarly for the second tree, right? So here we are calculating that, like if we state 1 of I is equals to 0, then c1 even plus plus, or else c2 odd plus c1 odd plus plus. Similarly we are calculating for the second tree, right? So here also we have calculated for the second tree, like we made it bipartite and how many nodes are painted 0 and how many nodes are painted 1. Now I have taken the max of C2 even and C2 odd, like whether more nodes are painted 0 or more nodes are painted 1. So I took max of them and I will try to connect, like let's say if number of 0 painted nodes are more, then I will try to connect that particular node for which we are calculating the answer in the first tree to some node which is painted 1, right? Because that distance is covered, one distance is covered, and if we want to make that even, like we have to calculate how many nodes are there at even distance. So that's why we and here that's why we connected to one of the adjacent nodes of 0. Like we will try to connect a node which is painted 1, such that for coming from one painted node to 0 painted node in the second tree, it takes one more distance. So that's why I have calculated this. Like if c2 even is greater, like whatever the max is there, and we will be adding that max into our answer, right? So here one condition you need to check, like I have taken this result variable, and if the node is painted 0 in the first tree, then I have taken uh, for the first tree I have taken all the 0 painted nodes, that is c1 even, or else if that node is painted 1, because in the first tree the answer is fixed, right? We can't change it. What we can change is how many nodes, how many maximum number of nodes we can connect with in the second subtree, in the second tree, right? So that's why. So if the node is painted 0, we will consider all the nodes which are painted 0. And if that particular node is painted 1, then we will consider all the nodes which are painted 1, because they will only form the pairs with even distance, right? And at last we will add our answer in the second tree for the current node, right? So this store of I stores like the mm, answer for node I in the first tree. At last we are returning our store. So yeah, that's it. We have been through all the problems. If you have any doubts, you can ask me in the comments. Thank you for watching.